It is section 8.7, numerical integration. For the evaluation of definite integrals, we studied the various techniques for finding antiderivatives. However, in reality, finding antiderivatives is not easy because those integrals are not expressed as a sum of elementary derivatives. When we cannot find a workable derivative, antiderivative for function f, we can partition the interval of integration, replace the function by a closely fitting polynomial on each subinterval, and integrate the polynomials part by part, and add the results to approximate the definite integral of f. This procedure is an example of numerical integration. In particular, Trapezoid rule and Simpson's rule are based on this procedure. And you can watch the project video by clicking this site. And here we'll consider another kind of numerical integration technique, which is called Gauss quadrature. Okay, let's go to the third subsection. Okay, here. Okay, let's consider this example. Find the points t1, t2 in the interval, unit interval, and weights w1 and w2 such that for given f, this approximation is accurate as possible. Okay, when we try to get accurate approximation, we have to start with a space. And let's consider polynomial space. Then for polynomial space, basis functions can be chosen in this way. 1, that is the first basis element, and t squared, and t cubed, and so on. So up to t to the n, and this will make a basis for polynomial degree of n. And once it is accurate, then it must be exact when the function f is now, for example, a constant 1. And at least for this one, it must be exact, right? So for that case, integral -1 to 1, f is now 1 and dt. That is the same as here for the right side, that is w1, f at t1 is 1, and w2 and f at t2 is again 1, right? Now also, okay, and secondly, if f is t, so linear, for linear, also it must be exact. Here, -1 to 1, t dt. That one is same as now for the right side, w1, okay. That is here w1, and ft1 is t1, plus w2, ft2 is t2, right? And thirdly, f is t squared, then integral -1 to 1, t squared dt, and right side must be w1, f at t1 must be t1 squared, because f is now t squared, and that is w2 and t2 squared. Okay, we'll write down one more, and f is t cubed, then integral -1 to 1 f of t, which is t cubed, and dt is same as w1 ft1, which must be t1 cubed, and w2 times ft2, that is t2 cubed. Now we have 4 variables to decide, so that we need 4 equations. So we made this 4, and we ask the approximation exact for these simple choices. At least for these choices, it must be exact. So in this way, we try to decide T1, T2, and W1 and W2. From these 4 equations, now we can get here another system of equations. Okay, integration of that one is 2, and we can simplify this one so that here W1 plus W2 equal 2 from the first equation. Second equation is symmetric interval and odd function, so it must be 0. And W1 and T1 plus W2, T2 must be 0, right? For third one, the integration of that one will be, okay, antiderivative is 1/3 t to the 3, and 1n minus 1. The subtraction must be here 2/3. Okay, that side will be W1 T1 squared plus W2 T2 squared. That is same as that. And for this one, now again, it will be 0. And W1 T1 cubed plus W2 T2 cubed equal 0. Okay, we have another system of equations. We have to solve that. You can manipulate these equations and to get the solution. However, for this here now, and we may consider that here symmetry. So there is no reason not to be symmetric. That means that here between -1 and 1, once T1 is chosen, then T2 is negation. And also for this one, now because of symmetry, the value must be the same. And that means that here from the first equation, here W1 and W2 are 1. Okay, once W1 and W2 are 1, then from this one we have T1 plus T2 equals 0, means that here T2 equal minus T1, right? Okay, now for that one, here W1 and W2 are 1, so the left-hand side becomes 2T1 squared. Right-hand side is 2/3, and divided by 2 and take a square root, so that so that here T1 will be, okay, so from this one T1 will be plus minus 1 square root of 3. Okay, so if we choose here T1 equal the left side minus 1 square root of 3, and T2 is negation, so 1 square root of 3, then we're done. Okay, these values and that values, we found everything. Now, along with this one, the fourth equation will be satisfied. And W1, W2 are 1, and here T1 cubed plus T2 cubed along with these values must be 0. Right? So we solve the n. Okay. We'll try to use these the variables to get estimation of this integral. Okay. Now we are using W1 is 1, W2 is 1. Now point for the function f, minus 1 over square root of 3 and plus 1 over square root of 3 if you try to get numeric value, then you can get this one. And now you can find also exact value. Antiderivative of cosine is a sine. So if you measure that one, then you can see here this quantity. So this one is good approximation, even though we are using 2 points and the evaluation and here add them. Now value is really good. Okay. Now for this one, we try to find the 2 points between -1 and 1. But this technique can be used for general intervals. For an arbitrary interval a to b, we may introduce a transformation. It's a kind of substitution or change of variable. Now b minus a over 2 t plus a plus b over 2, and x is defined in this way. Then once you make this transformation, then we can easily see dx is the same as now these coefficients and dt. Right? So that is now due integration for over arbitrary interval a to b. Then here now for this one, the transformation is made in this way. -1 goes to a and 1 goes to b, so that the corresponding points are here -1 and 1 in t domain, and x is now replaced by this term here, and dx is replaced by that. So we have this one. Now this whole thing is defined over -1 to 1, so that we can use the technique we considered here, so that now we can write in this way along with head notation, w1 fx1 plus w2 fx2. Here w1 hat, wi hat is now here rather than the earlier wi, it must be scaled. Because of that one, we have to consider this one. So this term is multiplied over there. And also for xi hat, and we are using just the transformation. It can be written in this way, but anyway, that is the transform the points, so that like that here. Okay, -1 to 1 pictorially. Here -1 to 1. You have for t1, t2. You have a -1 over 1/3 and +1 over 1/3. There are 2 points here now, and this is transformed to arbitrary interval a to b, so that the corresponding points will be located through this transformation. Okay, and if you measure the ratio between this and that, then exactly same ratio, because it's a linear transformation. Okay, but here the main point is that this Gauss Quadrature rule can be applied for general intervals. Okay. Now here we officially define Gauss Quadrature rule. The Gauss Quadrature for Q nodal points. Earlier we considered only 2 nodal points, but now general Q nodal points is defined in such a way that the approximation shows an optimal accuracy over the choices of nodal points and weights. Depending on choice of a space, it'll be a little bit different. However, basically they are the same. Earlier, when we tried to get wi and ti, we tried to use here standard polynomial bases. So if you are using the same the the standard basis, then you can get a set of nodal points and weights. Okay. Now, for this example, we'll try to use Gauss Quadrature rule and to evaluate, estimate this integral. And now here, and we try to use 4 subinterval, 8 subinterval, 16 interval when n is 4. Okay, that is now from 0 to pi over 2, and we make 4 subintervals. Okay, for that one. And now here, Gauss Quadrature rule is defined from -1 to 1. From here, for each subinterval, we make a transform here. Now, for that one again, we make a transform here, and transform here, and then transform here. Of course, for this standard interval, unit interval, you can define now Quadrature rule along with Q is 1. Then, of course, over there, you'll choose only center value 0. And, of course, after transformation, is corresponding to the midpoint of each subinterval. Now, we already finished when Q is 2, and when Q is 3, also you can make quadrature formula, and then that will be transformed to each subinterval. Now here, we'll use the Gauss Quadrature rule to estimate the integral with n is 4, 8, 16, and q is 1, 2, 3. So that there are 9 combinations. And we'll compare the estimates with the exact value. So we'll try to measure the error and compare accuracy with that of the Simpson's rule. Here we have a note. When q is 1, then the Gauss Quadrature rule becomes the midpoint rule, right? Okay, here, along with a computer program, we'll test it. Now, function is sin x plus x cubed, and beginning point is 0, end point is pi over 2. And if you make integration, then exact value is given in this way. Now, when n is 4, we can do it over there. And after changing this one to 8 and 16, you can do run this code. Now, for q from 1 to 3, now iteration is done along with this function f, a, b, and n and q are inputs. And so that here, GQ will save 3 values, and for that, here exact value will be subtracted and divided by the exact value. That becomes relative error, and the printout will make 30 values. Okay, and the format is short engineering format. Now, this is a main program, Gauss Quadrature.m. Okay, here for input, n is the number of subintervals, and q is the number of quadrature points in each subinterval. In initial setting, we got h, b minus a over n, and we have a partition, and there are n plus 1 points, and so that there are only n subintervals start from x1. In MathTalent, the index starts from 1. Now, standard T and W can be gotten in this way. When Q is 1, then midpoint, and -1 to 1, midpoint is chosen. Of course, at the moment, the weight must be here 2. Now, when Q is 2, we got these values already, and weight is 1 and 1. And Q is 3, then here again you can see symmetric is well known in the literature, and 0 is the center point, and we have these two. So the 3 point and corresponding weight is given in this way. Okay, now along with that, here the t must be transformed to x, and also w must be scaled. This line is corresponding to here. That is from the standard weight, it must be scaled. And that is h over 2. And then now from standard point, 1 is added and h over 2. And here left edge point, later it will be used, but in the scaling we consider only this portion. So that is exactly this one. And then now the beginning point for each portion, n is moving through the subinterval. So the partition 1, partition I is the beginning point of each subinterval. So that is now a is added in the mathematical formula, and function value is now evaluated, and the function values and weights are multiplied element-wise and summed, and then added to the value v, so that after finishing this iteration whole through each subinterval, the integration is made and added to over the whole subinterval. And here, when n is 4, this is output. For q is 1 and 2 and 3. And when n is 8 and n is 16, we have such output. As you can see here, the accuracy is really good. And the computational course is almost the same as now Simpson's rule. And when you are using Simpson's rule, then n is 4, 8, 16, you have such relative error. Now, for this case, it's better. The Gauss Quadrature rule has some optimality so that it can be better. For this example here, it's really good. Yeah, right? Okay. This is the end of the section. Thank you.